Okay, now we are going to shift to a new topic. Common and natural logarithm functions. Actually, we've spent the last couple of days working on inverse functions, and that is why we had to do it, because here we go. Logarithms are exponents, and what they actually are is logarithm functions are inverses of exponential functions. So if we look at this first statement, every exponential function, a to the x, a bigger than 0, and a not equal to 1, is 1 to 1 by our horizontal line test. And we graphed several of those before we did the inverses. But now we know it's going to have an inverse, and we get to use this special notation. Okay? And the logarithm function is our inverse. And so what we can say is, let's remember that we have that if we have an x on an inverse function, it came from the y coordinate on the original function. And if we have a y on the inverse function, it was actually the x on the original function. So remember our x's and y's. Swap. Yep. All right. Next.
I'm going. Here we go.
Okay. So the definition of a logarithmic function says, let a be a positive number not equal to 1. And a logarithm function with a base of a. Look how that a hangs off. It's the base. It's in the basement. Okay? And it says, if we just read this sentence, log base a of x is y. And what this implies or means is that a, my base over here, see the a in the basement? It is now the base of my exponent, y, and that's going to give us x. Now let's go back and look at this again. What is our key phrase for today? A logarithm is an exponent. There's our exponent. Our exponent is y. Our logarithm is our exponent. So the exponent is y.
Okay, so the way I like to remember it is if you have log base a of x equals y, I like to use a cool little thing I like to call the ear. You start here and then you draw the ear. There's the earlobe, and there we go. So basically you write it as you draw it. So it's base a to the y equals x. Okay, so base a over y equals x. And it works backwards too.
Let's write a little problem. Come down here. I have an idea. Let's write log base 3 of x is equal to 2.
No, 2? Okay.
Yeah. Okay. So 3 to the second equals x. Remember, a logarithm is an exponent. So if you read this statement, this mathematical statement is a sentence. It says log is means equals in math 2, so 2 is our exponent. And if you also look at your log equation, the 3 is hanging down in the basement, so it is your base. So 3 to the second is x. Of course, you could now figure out that x is 9. You don't need a calculator for that. But what that means is log base 3 of 9 is just a funky way of writing the number 2. Okay? Now, common logs are logs with a base of 10. You've used those probably in science, so we're going to start out with that, and it's important to understand that when you do not see a base written, it's understood to be 10. Okay? So, how would we do log of 10? Well, that literally means log base 10 of 10, so let's make sure we really understand that. All right, and what would that equal? Well, that really means 10 to what power gives us 10? Well, what would that power have to be? 1. So that is the number 1. So let's think about the next one. Now we can start thinking about making an equation. So log of 1,000 is x. Now what is our base?
10.
And so 10, use the ear, to the x is equal to 1,000. Now we're not going to use the calculator on here because there's a relationship between 10 and 1,000. 1,000 could be written as 10 cubed. So if 10 to the x equals 10 cubed, it's pretty clear that x has to equal 3. Oops, there is my phone. Let me silence it.
All right, so here I have 10 to what power, this is equal to x. 10 to what power gives me 0.1. Well, 0.1 is really 1/10. So that's 10 to the negative 1 equals 10 to the x. So this tells me that 10 to the x equals 10 to the negative 1, so x equals negative 1.
Okay. So let's think about the next one. We want to write this. We can recognize that that would be equals x, so 10 to the x equals 10 to the 1/3. There you go. X is 1/3.
So x is 1/3.
Equals x. So 10 to the x equals 0. We can't have that because 10 raised to any power is going to be at least some kind of number, not 0. 10 is a positive number. If you raised 10 to the negative 378 million, it would still be a positive number. So we have no solution to that. Not possible. So we just say that that's undefined. And the real way to think about this is, what number could we actually raise 10 to give us 0? Nothing. It just can't happen.
Okay. So, solve each equation by using an equivalent statement. Well, we know that this is a log of x equals 5, so this is really log base 10 of 5 equals x. Oh. All right.
And remember, log is exponent, so 5 has to be our exponent. See how that works?
So 10 to the 5th is 1, 2, 3, 4. I put the, yeah, okay.
Oops.
There.
There we go.
There we go.
Okay.
So 100,000.
So that one didn't need a calculator. However, let's look at this one. We know, if we just think about it, that 10 to the 1 is going to equal 10, and 10 to the 2 is going to equal 100, and the number we're looking at is 10 to some power equals 52. So isn't it clear that x would have to be a number between 1 and 2, since our 10 to that power is 52, and 52 is between 10 and 100? Well, sadly, you don't have the ability to do this without the calculator. So the way we actually compute this on the calculator, let's convert it to a log function, okay? And write this log. We don't need to write base 10 because it's understood. Log of 52 equals x. So we're just finding log of 52. So you would, there's the log button.
Press your control button first to access the stuff in the upper pieces. It's not actually on the button. So control and then the 10 to the x button will get you log base 10.
And why do you think that is? Because log is the inverse of 10 to the x. And when you do that, we want you to do this on your own calculator, but you should get x to be approximately 1.716, and think about it again. Did not we expect a number between 1 and 2?
Okay. All right, so first problem, go to section 5.4 and work these problems. These really don't take very long, as you can tell. They're really fast.
And no calculator.
All right, so natural logarithms. Remember last chapter we talked about this base e, this number e, that's a special number. Well, if we have a logarithm with a base of e, we call it the natural logarithm, and it's denoted by ln of x, natural log of x, okay? And that equals log base e of x. So instead of writing all this crazy stuff, we write ln of x.
And I always have students that think that ln they see there on the calculator is in, and they think that's an inverse. It's not. It is natural log. Now, why do they call it natural log? Because in French, which is the people that develop logarithms, it is called logarithme naturel, hence ln.
Okay, so use a calculator to value the following, but calculators are not necessary on A, B, or C. So we're going to do that first.
Now let's just do something really basic here that'll be important later. ln means log base e of e to the third equals x. Now, if our logarithm is an exponent and we use Ms. Meller's ear trick, do you see that e to the x equals e to the third? So what's x?
X equals 3.
Now let's look at this. Let's go back and look at what this means. Do you see that if these two bases are equal, that your answer is going to be that exponent? That's going to be important in some of the homework problems. Okay, how could we think about this one?
So this really is equal to x. So if I think about it, this is actually log base e of 1 over e to the fourth equals x.
And you know, to be honest with you, in the future, we don't want you to actually write this step out anymore.
This is not necessary, okay?
Yeah.
So I'm just reminding you that this is base e. So e to the x
So
equals 1 over e to the fourth. And how do we get a fraction? Well, a negative exponent. So that's e to the negative 4. So e to the x equals e to the negative 4. So x equals negative 4. Oops.
I bet you can do the next one pretty easily.
Well,
E to what power gives 0? Well, do you remember that e is about 2.71828? So it is a positive number. You cannot raise a positive number to anything and get 0. You can get close to 0.
The only number you can raise to any power and get 0 is 0.
And yeah.
So,
So the answer, without doing any work, is undefined.
All right, so now the next ones we have issues because this is telling us e to what power gives us 10. Well, e is a weird number, and to get 10, I'm going to have some issues.
Well, we could think about, we are still going to have to use our calculator, but think about this. E is about 2.7, right? So that's a little less than 3, and we know that 3 squared is still less than 9. So we know that x needs to be some number bigger than 2 probably. Okay?
But how do we get this? If I want to just write ln of 10 in my calculator, I would press Control, and then the e to the x button gives me the natural log. Okay, so I would press Control and then e to the x, then 10, and that gives me that x is approximately 2.302, or if you truncate, or 2.303 if you round.
And I think you have to be careful with your parentheses, so you'll have to make sure it's ln, the parentheses comes up, you type in your 10, and then you close off the parentheses. So go ahead and do this one all on your own, and we'll put the answer up.
Okay, hopefully you paused. So we have ln of 203, all right, gives us 5.313 approximately.
There you go.
All right. So here we're going to solve each equation by using the equivalent statement. An ln of x, I don't know what to do with that, but I do know that ln is base e, so e to second power is x. Remember?
Notice that we have written inverse functions here. We have a natural log function, which is the inverse of the e.
So e squared is approximately 7.389.
Mm-hmm.
Okay, so using the ear, I'm going to go ahead and draw that, and I've got ln, because it's base e, of 8 equals x.
Boom.
So that gives me x equals 2.079.
So make sure that's a 2. Yeah.
X and a 2.
Yeah. Make sure you do those on your calculator and make sure you can get those answers. That's really important. Okay.
All right. So using section 5.4, go to number 28, 29, 30, 31, and 32. Do not use your calculator.
Yeah, these are some of the ones that are like the non-calculator problem. We'll get calculators in a minute.
All right, so notice that we've talked about inverses for the past 2 class periods. The exponential function we talked about last chapter, it starts to come over to the horizontal asymptote of the x-axis, and it goes up like this. Well, a logarithmic function is reflected over the y equals x line, and its vertical asymptote is at x equals 0, right there.
Yeah, and this is important because if we write the horizontal asymptote for exponential, it is y equals 0. And remember that with inverse functions, all of the properties of x and y switch. So logarithm functions, your basic function before you do any shifting from the left to the right, has a vertical asymptote at x equals 0. And remember, we did a couple of problems that said there's no way that x can be a negative number. So.
All right, so the domain of an exponential function is all real numbers. The domain for a logarithmic function is only positive numbers. Okay, so, and the range for an exponential function is only positive numbers. So their domain and range is swap. So the domain for this one is the range for this one, and the range for exponential is the domain for logarithmic. Okay, so everything swaps.
Yeah, notice that an exponential function is increasing. This is in its most basic form, and so its inverse also has to do the same, which it increases. And okay, and then here's some sample points for you. So it just gives you some stuff to look at. All right, so now we're going to look at doing transformations. Okay, so one of the things that's really important is, this is really critical, is that the argument x plus 4 always has to be positive. That argument, so we want to write x plus 4 must be positive, so x has to be greater than negative 4. That's a real important thing to figure out. Now let's go back and look at how our shift is from the original function. Okay, our original function has the x-intercept at 1, 0. And now let's go back to the problem. And what would make that right there, what would make that quantity 0 is -4. So look at that. That is getting shifted 4 to the left. So what we have is a horizontal shift left 4. And look at the coefficient of this. It's going to make the y values steeper, okay, because we have a coefficient of 3. So it's steep. The y values are steeper by a factor of 3. Now you're asked to give your domain and your range. Your domain, we just figured out, x has to be greater than -4, so we would write it in interval notation. And if you remember the graph from the previous slide, which is on your paper, the range is all real numbers. Okay, let's look at our next one here.
Okay, so this one we're going to describe the transformation of the natural log function. And here
we want to actually do a little work.
Okay, so
if we factor a negative out of this, we got ln of negative parentheses x minus 4 plus the 2 afterwards. Okay, and so what you can see that we have here is it looks like we're going to shift right 4, and that negative means we flip over the
y-axis. Okay.
Remember, when you have the negative inside, it does that. And we're going to shift this up too. And what is our domain? Well, our domain, 4 minus x, must be positive. So write 4 minus x must be positive. And so solving that, we would just easily move the x over. So 4 is greater than x. I don't like that very well. I have to kind of look at that as x is less than 4 to help me see it. So that would mean that we are negative infinity to 4. And once again,
range is all real numbers. Okay.
And all right, last thing that we're going to do is a nice little word, a nice problem. If you invest money at that rate, compounded annually, then this function t of r gives the time in years that it would take to triple. So how long is it going to take to triple an investment of $500 at 5%? Well, our rate is 5%, so we're looking at t of 0.05, and that's going to equal ln of 3 over ln of, and it's 1 plus 0.05, which is ln of 3 over ln of 1.05. And again, be careful with the parentheses. It's ln of 3 parentheses, divide by ln of that. And do it on your calculator, but you should get about 22.517. And that means that we're talking about 22 and a half years. So it's going to take about 22 and a half years for the money to triple. All right. What annual interest rate is needed for that investment to triple in 15 years? Well, we have to take our function, ln of 3, over ln of 1 plus r, and set it equal to 15. Now, one way we can do that is to draw the line y equals 15. And when you go graph the ln of 3 over ln of 1 plus r, except you have to use an x in the calculator, it looks like that. And you can find the point of intersection, which is right there. Also, you can go to the solve feature on your calculator, and you should get right here, r is about 0.075989. 0.075989, which is, the question is, what's the rate? The rate is about 7.6%. There you go.
Okay. So, go to section 5.4, do these problems. They're calculator only in 65. Everything else, no calculator. All right, so by 8 a.m., one new thing you learned, one good question, 2 old things that are important for this material. What?
I said there's nothing else. We have an extra slide, but we don't really explain.
All right, that's it.
Have a great day. We love you.
Bye.